In section 2b, we will discuss numerical descriptions for univariate data. So we're still dealing with a single variable here. Of course, now we're going to start calculating some basic descriptive statistics. Some of these you'll be familiar with, some of them you're probably not. But there are three main types of measures that we deal with in this course. We deal with measures of center, which I'm sure you're probably familiar with, the mean, median, and mode. Then we deal with some measures of position. We talk a little bit about that idea. We focus on really the quartiles and the 5-number summary. And then we will talk about measures of dispersion or measures of variability. Variability is a very important idea in statistics, so it's a very important topic as we move forward in the course. So let's start with this example. We are going to suppose that we take a random sample of 8 fuel-efficient cars and record the gas mileage. We're going to start with the measures of center. So you should have already read through these in the notes. And like I said, you've probably seen these before, but we may talk about some things that you're not aware of. So the mean. These are all measures of center, measures of a typical value, measures of average. When most people talk about an average, they're talking about the mean. In statistics, we're a little more specific. We don't commonly use the measure of average other than kind of as a general term. But whenever you typically hear average, people are talking about the mean. When they talk about other measures, they typically identify them by name. So the mean is your typical average, is typically what people talk about when they talk about an average. So it's a pretty simple calculation. You just add up the data values and divide by how many there are. So when you start to do these descriptive statistics, I highly recommend that one of the first things you do is just to make sure that you put your data in order. And of course, you'll need the sum of the data for the mean because we calculate the mean by adding up the values and divide by how many there are. So it's always kind of nice to just start by listing out your x values. It's nice to put them in order because when you calculate the median and measures of position, you'll need them in order. So it's kind of nice to start out this way. Just list out your x's. Your x, of course, is our variable. That's our data values. And then I usually just sum those at the bottom. You will notice the capital sigma. It says sum of x. That's how we typically write that. That capital sigma, if you're not familiar with that, in mathematics, that means sum, and we use that symbol a lot. So the way we read that is we say the sum of the x values is 301. That's just the sum of our data. So to calculate the mean formula looks like this, and you can see the calculation for this example there as well. But the way we denote the mean is by x bar. I'll typically say x bar. It's x with the line over top of it. That does specifically represent the sample mean. It is important to note in this section we are talking about sample values, so we're talking about statistics. We're not talking about parameters. Remember, parameters are numerical characteristics of the population. We're not dealing with population information here. We're dealing with sample information. Statistics are numerical characteristics of your sample, and that's really what we focus on here. It's the much more common scenario. Typically, you don't have population values as we've already talked about. We don't typically have the whole population. We typically have a sample instead. So we take that sample and we describe it. That's the more common scenario here. So when we calculate these values, they are statistics. Statistics are denoted differently than parameters. So the sample mean does not have the same notation as the population mean. So it is important to notice that when you see that x bar, that does specifically represent the sample mean. So we've already said we calculate the sample mean by adding up the data and dividing by how many there are. So you can see sum of x there. That's the sum of your x values. That's how we write that. So the sum of x just means that 301 value, the sum of those x values. And of course, n is always your sample size. So there are 8 data points here. So we just take the 301 divided by 8, and that gives us that 37.625. Our second measure of center is the sample median. So this is why it's important to put the data values in order. The sample median, there's not really a formula for the sample median. The sample median is basically your center value. So the center value does depend on whether your data set is odd or even. If there's an odd number of data points, then it's really simple because there's one data point that is right in the middle, so that data point is your median. If, like in this case, there's an even number of data points, then you do actually have to take the mean of the two center data points, because actually the median is technically in rank order between those two center data points. So in this case, you can see that the two center data points are both 37. So even though they're the same value, the first 137 comes before the other one in rank order because we have to order these. And you want to make sure you include both data points in that ordering. So technically, the median in terms of position comes between those two values of 37. So the way that we get that median is we just find the value in between those, which of course in that case is nothing more than 37 because they are the same. So basically you just average or take the mean of those two values, and when you do that you get 37. You'll notice that the median does have notation as well. I'll typically say x tilde. It's x with the squiggly line over top of it, even though there's no such thing as a squiggly line. But anyway, that's a tilde, so it says x tilde is 37. So the first thing, of course, with the mean and median you have to be able to do is you do have to be able to calculate these values. But it's also important to know when to use each one, kind of what their characteristics are, and we'll talk more about that as we work through, but let's just talk a little bit about that now. One of the things that distinguish, or the big thing that distinguishes between when you should use the mean or the median, is it depends on whether or not you have extreme values in your data set. The shape can also have an effect on the mean as compared to the median. In terms of extreme values, so it's one of these things that you will sometimes see, like if we took everyone's income in the class and we describe that information with the mean and the median. Well, which one would be a better measure? And the answer to that is really it depends, and it kind of depends on what the data looks like. What we would find is if everyone's income in the class was very similar to each other, then the mean would probably be the better estimate for the center. However, something that can happen is if you have like Anthony Davis in the class and his income is way, way higher than everyone else's, then what can happen is that value can really affect the mean. And the mean will be pulled toward that high value. And in a case like that, what will lots of times happen is the mean will actually be bigger than every data point in the data set except for Anthony Davis's data point, because his is so high that it pulls the mean really, really high. The median doesn't have that same effect. It is not influenced by those extreme values like the mean is. So we do say that the mean is sensitive to extreme values and the median is not. It's one of the cases where you'll see the median used. If you ever hear them talk about income, you'll notice that they never say average income whenever they report it. They always say median income because the median is a much better measure. If you look at the mean income in the United States, it's really, really high. But it's because of that really top 0.1% of incomes that whenever you calculate the mean is really, really high, but it's in no way representative of what a typical person makes. So the median is a much better measure. Let me just talk about it in terms of this data set. And these values are going to be unrealistic, but let me just talk about it so that you can see it a little bit mathematically. Just think about what happens if we take that value of 45. 45 is the highest value in the data set. But let's just suppose that that value is not 45. Suppose that value is 100. If that value is 100, notice the median does not change, right? Even if we change that value of 45 to 100, the median is still 37. However, the mean is going to be way higher because that sum of the x values is going to get higher. If we change that value to 1,000, it still doesn't change the median. So notice it doesn't matter how extreme that value gets, it doesn't affect the median, which is why we say the median is not sensitive to extreme values. However, the higher that value gets, the more and more it's going to affect the mean, which is, of course, why the mean is affected or sensitive to extreme values. So it's important you distinguish. The general rule is if you have extreme values in your data set, the median is a better measure. If you don't have any extreme values, the mean is a better measure. Technically, the mean is a better measure because there's less sample-to-sample variability in the mean than the median when there's no extremes. You don't really have to know that at this point. We'll talk about that later on when we get to sampling distributions. But you do need to know that when there are extremes, the median is a better measure. When there are not extremes, the mean is a better measure. Okay, the third measure is not commonly used. It is the mode. The mode in this case, the mode is just the most frequent score. So all these data points do occur once except for 37, which occurs twice. So the mode is simply 37 here. We don't really have any common notation for the mode. You can look at different books and they'll give you different notations for the mode. It's not used mathematically a lot, so there's really never become a standard notation for the mode. So we'll just call it mode. We don't use it a lot in this class anyway, but the mode here is the most frequent score, which in our case is 37. So there are some big issues with the mode, which is why we don't like it. For example, if one of those values of 37 changed to 39, then notice the mode totally changed. If one of them changed to 41, again, the mode totally changed. So just sometimes by just randomly selecting one data value instead of another, you can really change the mode, especially when you're dealing with data sets where the frequencies across values are very similar. Sometimes just by randomly selecting one value instead of another, you might really change your mode, and we don't like that. It's not a very stable estimate in that sense. Another issue with the mode is sometimes we'll say there's more than one. So what if there's two 37s and two 39s? Then you have two modes, 37 and 39. So we can say there's two modes in that case. It can also be the case where all the data points are different. If one of those 37s was a 36, then you have every single data point that's different. And in that case, we would commonly say that the mode does not exist. So the other issue with the mode is it doesn't always exist, or there's more than one, depending on how you think about it. Most of the time when there are going to be a bunch of modes, we just say the mode does not exist. If there's only going to be a couple, lots of times we'll say there's 2 or 3 modes. But that's really not what you want. Really, you want a single measure that's going to give you the center of the distribution. And that's not exactly what we get with the mode. So the mode is not our favorite choice for center. So why do we talk about it? So the mode is useful in one case, and this is where you should use the mode. What if we have a college and we say, I've actually heard this before. I was at a college before, and one of the things that they said in their intro was they said our average student is female. So if someone tells you their average student is female, what does that tell you? Well, they obviously didn't take a mean. They didn't take a median, because you can't take a mean and median for a qualitative variable. But what you can do is you can take the mode. And that's commonly where the mode is used. If we say something like the average student at the college is female, then all that really means is that just means there's more females than anything else. That is the largest group. So the benefit of the mode is it can be used for qualitative data, and that's when we will use it. So those are our 3 measures. The mode's used for qualitative data, the median is used for quantitative data when we have extremes, and the mean is used for quantitative data when we do not have extremes. There's one other thing that we can do with the mean and median, and that is, and I already mentioned this, but the mean and median are affected differently depending on the shape of the distribution. You can actually tell whether or not there's any skewness in a distribution by comparing the mean and median. So in this question, I say if x bar, so that's the mean, is greater than x tilde, that's the median, what's the shape of the distribution? So if x bar is greater than x tilde, then that actually means that your distribution will be right skewed. So let's just look at a picture of a right skewed distribution. So if you think about what the mean and median represent mathematically, well, this is a curve, which we commonly use to represent data. We also use histograms. This is just a smooth curve, but you read it the same way as the histogram. You look at the highest point, and then you can see the longer tails to the right. That's what a right skewed distribution looks like. So in a right skewed distribution, or in any distribution, the median basically divides the data in half, right? Exactly half your data is below the median, and exactly half the data is above the median. So if you think about that, in a curve like this, it would basically mean that half of the area under the curve is to the left of the median and half is to the right. So whenever you put the median on there, the median is simply going to divide that area into two halves. The mean is a little different. The mean is technically the mathematical balancing point. So you can do this kind of thing in physics where you actually, in two-dimensional space, figure out what point on this graph would actually balance it. And whatever point on this graph would actually balance the left and right, then that point is the mean. And you can see, if you think about a balancing point, the points that are that longer tail to the right, the fact that it's got that long tail to the right, those points are going to be heavier because they're further away from where you're balancing than the points that are close to what you're balancing, to that balancing point. So those extreme values, or that really right tail to the right, is going to affect the balancing point more than points that are close to the center, right? So if you think about that, essentially what's going to happen is that long tail to the right is going to pull the mean more toward that direction, or toward the longer tail. It's the same thing that happens with extreme values. If you have an extreme high value in your data set, the mean is pulled toward that extreme high value. The mean is always more affected by values that are further away from center. So since in a right skewed distribution you have this long tail to the right, the mean is going to be more affected by that long tail to the right and is going to be pulled to the right of the median. So if the mean is pulled to the right, that means bigger than the median. That means you're going to have a right skewed distribution. That's the way it works, and that's the way I recommend you think about it. Always think about which direction is the mean going to be pulled. And the mean is always going to be pulled in the direction of the extremes or the longer tail. That's the way you compare these. So in a right skewed distribution, the mean is bigger than the median. If we reverse it and we say if x bar is less than x tilde, what's the shape of the distribution? I'm sure you can guess this. That's got to be left skewed. And it works the same way. In this case, the median is going to divide the area in half. The mean is going to be pulled, the balancing point is going to be pulled to the left because of that long tail to the left. It's going to be pulled toward those values to the left. So the mean is going to be smaller than the median in a left skewed distribution. What happens if they're equal? Now, in reality, when you actually collect data, you can't expect the mean and median to ever be really perfectly equal. But lots of times they will be really close. So let's just start with what if they're perfectly equal. If they're perfectly equal, then of course your distribution is perfectly symmetric. So in a perfectly symmetric distribution, if you think about what we just talked about, the point of symmetry is the point at which the area is going to be divided in half. It's also the point at which this distribution will balance. So in a perfectly symmetric distribution, the mean and median will be equal. Now, like I just said, they're never really going to be exactly equal. But if they're really close, then we still can say that this distribution is fairly symmetric. So we tend to throw that qualifier on there and say fairly symmetric. But whenever the mean and median are close together, we have a fairly symmetric distribution. Of course, then the question becomes, well, how close do they have to be together to be able to say that it's symmetric? And when are they far enough apart to have to say it's left skewed or right skewed? And that is a bit of a judgment call, and you have to make these judgment calls in statistics. I will say the best way to get good at when to say something is symmetric or right skewed or left skewed, or in general, the best way to get used to making judgment calls is just to do statistics for a while. The more you do it, the more comfortable you get with when is this actually going to have an effect on my results and when is it not. So when do I really have to deal with the fact that it's skewed as compared to symmetric? So without that, you will just have to make a judgment call. And in those judgment calls, of course, it's important that you defend your answer. If you say that the mean is bigger, so it's right skewed, then just say it's right skewed, the mean is bigger. That is a good explanation as to why that occurs. Or you can say these are close together, so I feel like it's fairly symmetric. So just make sure that you're able to defend those answers and understand why you're identifying it as you are. It'll take a little time to really get good at distinguishing when to say it's skewed and when to say it's symmetric. There's some measures that we can look at in order to determine that beyond what we just look at in this class. So if you do this for long enough, you get a better feel for when to say something symmetric and when to say it's skewed. So those are your measures of center and some of the uses of those measures of center. So we're still going to use the same example, but now we're going to start talking a little bit about measures of position. And we don't do a lot with measures of position, but there are a few that we talk about. One of the things that we talk a little bit about is percentiles, which we don't actually calculate percentiles from a data set. But it is important to just understand what a percentile is. A percentile is probably the most common measure of position that people see. And the reason being is because lots of times, like when school-age kids take a standardized test, they'll get results that will say stuff like, this student scored at the 95th percentile in math. And if a student scores at the 95th percentile, what that tells you is they did better than 95% of their peers on that exam. Now notice, it's a measure of position. It tells you they did better than 95% of their peers on the exam. So it tells you where their score was relative to everyone else's. It doesn't necessarily say that they did good on the test. Technically, they could score at the 95th percentile and do terrible on the test. As long as they did better than 95% of their peers, they're at the 95th percentile. That's the idea of a measure of position. We're measuring their position relative to everyone else's. We're not really concerned exactly, we kind of are, but we're not really measuring how they did on the test. We're just measuring how they did on the test as compared to everyone else. We're looking at their position relative to their peers. Now the ones that we will calculate, the big ones that we calculate are the quartiles. And we do this in part because we'll look at a graph called a box plot, which is essentially a picture of this 5-number summary. So the 5-number summary starts with the quartiles. The quartiles, there are 3 of them. It takes 3 points to divide a data set up into 4 equal parts. So essentially the quartiles divide the data set up into the bottom 25%, the next 25%, the third 25%, and the final 25%. So essentially we're going to have 25% of our data divided up into these 4 parts. And we need 3 points or 3 quartiles in order to do that. So of course, in order to deal with measures of position, we need our data in order. So this is nothing new, just a list of our data, and I also have the sum down there at the bottom. We don't really need that for the 5-number summary, but for the 5-number summary, we're going to start with the quartiles. So the way this works is you always start in the middle and then you work your way out. So always start in the middle. So start with Q2. So Q2 is the point, it's the same as the 50th percentile. It basically divides the data in half. So the nice thing about Q2 is exactly the same as the median, because the median also divides the data in half. So always start with basically your median, which is your Q2 value. So Q2 divides the data in half. It's the same as the median. So if you know how to do the median, you know how to do Q2. So Q2 is actually the 37 between the 2 37s that you see there in the data list. So it divides the data in half. You have those 4 data points that are below this median, and then you have 4 data points that are above the median. So now you've divided your data set in half. You started with 8 points. Now you have 4 lower points and 4 upper points. If we look at just those 4 lower points, and then we calculate the median of those, that will give us Q1. So if you look at those first 4 points, you'll see the 2 middle ones are 34 and 35. So if we just take the mean of 34 and 35, we get 34.5. So that is Q1. Q3 works the same way. You look at the last 4 data points. you'll see the two middle ones are 39 and 41. So we just take the mean of those two and we get that Q3 value of 40. So notice that has divided our data set up into 4 equal parts. We basically have 33 and 34, then we have Q1. We have 35 and 37, then we have Q2. We have 37, 39, then we have Q3, then we have 41 and 45. So we basically have 2 data points in each section, in each portion, 25% portion of how we broke this up with the quartiles. So that is the start of the 5-number summary. Once you get to the quartiles, the last thing that we do is notice we don't have an endpoint for the lowest 25% or the upper 25%. So what we do finally is we just add the minimum value or the lowest value in the data set and the maximum value or the highest value in the data set. The low value here you can see is 33. The high value here is 45, and that is our 5-number summary. So that's really all there is to the 5-number summary. Start with the median, start in the middle, Q2. That divides your data set in half. Don't include the median. If the median is actually a data point, don't include that in the lower half and upper half. However, in this data set in rank order, the median is actually in between those two 37s because there's an even number of data points. But if there's an odd number of data points, the median will be a data point, so you don't include that. You just have half below and half above. And then you take that lower half, the median of that is Q1. The upper half, the median of that is Q3. That gives you your quartiles. Throw the low and high in there. That gives you your 5-number summary. The process always works the same whenever you go through and calculate the quartiles. Okay, so those are our measures of position. Those are the big ones that we talk about. We'll talk about percentile sum, but the ones that we calculate are really these quartiles along with the median. And like I said earlier, we'll look at a graph I think in the next section where we basically graph these data points, and it's a good way to look at data. So the last thing we need to talk about is really important. It's the idea of variability or dispersion. It's how do we measure how spread out a data set is. So most commonly, when you describe a data set numerically, we give 2 measures. We give a measure of center. We say, here's the center. That's typically our first measure, is a measure of center. Here's the center of the distribution. The second measure that we typically give is a measure of how spread out the data is. So I'm going to start with a couple that we're not going to use a lot, but since we already have the quartiles up here, I'm actually going to start with what's called the interquartile range. A range is not the best measure, but an interquartile range is actually a better measure than just a typical range. So the interquartile range, we abbreviate IQR. IQR is simply Q3 minus Q1. So you do have to get Q3 and Q1 correct in order to get this right. But the interquartile range is nothing more than just taking the Q3 value, subtracting the Q1 value. You can see here for this data set that's 5.5. So basically what IQR gives you is it gives you the range of the middle 50% of the data. That's something that's of course easy to see whenever you look at the graph that we're going to create based on these quartiles, as you see commonly that middle 50% of your data. The other kind of range that we'll look at is just a typical sample range, which is just the high minus the low. The high minus the low, of course, in this data set is 45 minus 33. That gives us a range of 12. So those are the 2 ranges that we look at. I do want to just talk a little bit about them. It is pretty common that you'll hear people when they give presentations, they'll hear people tell you what the range is. The range is really not a very useful value in most cases. It's not a very good measure of dispersion. It's actually something that I like to talk about because it's overused and it's something people will throw out there, but it's not really a useful value because just think about it. So suppose I have a data set of 1,000 points. I'm going to describe the variability in this data set by only picking 2 of those points, just the highest and the lowest value. So not only am I just picking 2 of these points, I'm picking the most extreme values in the data set, just the high and the low. And then I'm subtracting them and saying, this is a measure of dispersion. It represents how much variability I have in this entire data set of 1,000 points. That doesn't make much sense, and it's not a very useful value. Anytime you have 1,000 data points and you're basing a measure on only 2 of those data points, well, you pretty much know that's probably not going to represent the data set as a whole very well. The only time that the range is a pretty good measure is when you have a perfectly symmetric distribution. And of course, that's not that common. It's very uncommon that you get perfect symmetry when you collect data. The interquartile range is a little better because it does get rid of the issue of extreme values. Because the range, if you have any extreme values in your data set, is totally based on just those extremes, the high and the low. The interquartile range does get rid of that issue because you're only looking at the middle 50% of the data. So you're basically getting rid of the extremes in terms of this range. So it is better than a typical range, but it's still not as good as the measures that we're commonly going to use in statistics. So let's talk about what we typically will use when we describe a data set. So we will use what's called the variance and the standard deviation. And these are very common and very important values in the field. They go together. So you have to calculate the variance before you can get standard deviation. So we're going to start with the variance. Again, these are sample values. So this is the sample variance. So the sample variance represents the average squared distance the data points are from the mean. That's technically what it represents. It's the average squared distance the data points are from the mean. So this is actually in squared units. And because it's in squared units, whenever we go to use the formula, you're actually going to need 2 sums and not just one. You're actually going to need the sum of your x's and the sum of your x squared. So this is really, really common in statistics. You'll see this a lot. You'll see lots of times that when you calculate things by hand, you need not just the sum of your x's, but you also need the sum of your x squareds. This is the first time that you see this. So if you look over there to the right side of the slide, you'll see that I have that same first column that you've seen. Just that list of your x's. And then at the bottom, you have the sum of the x's, 301. Well, the other thing that we commonly need is notice that next column is just x squared. So this is really simple to do. You just got to be careful not to make any mistakes. It's a little tedious, but it's really simple. To get the x squared, you just simply square your x value. You just square your data value. So you square 33, you get 1,089. You square 34, you get 1,156, and so on. So we just get that list of x squared values. And then at the bottom, you'll see we write sum of x squared. That's 11,435. So when you calculate statistics it's pretty common that you need not just the sum of your x's, but the sum of your x squared. So you just create these 2 columns, get those 2 sums, and then once you get those 2 sums, along with your sample size n, which we know is 8, then we have everything we need in order to calculate variance. So my recommendation is before you ever even think about the variance formula, you do this. You create a list of your x's, sum the x values, and get the sum of the x's. Create a list of x squareds, sum that column, get your sum of x squared values. So we have that information. We know the sample size is 8 here. So now we can use the formula. So let me just show you the formula first, and then I'll talk a little bit about why we do this. Why do we have squared units? Because that seems a little odd. Why would we want things to be squared? Okay, so the first thing you'll see is the notation. The notation is s squared. So the squared, of course, represents the fact that variance is not in the same units as our original data. It is actually in squared units. So we write that as s squared. So the formula, the computational formula, and there's a couple different versions of this formula. There's a conceptual formula that comes from the definition, where we basically just take the x values, subtract the mean. That gives us the distance from the x values. We square those and we average them. That's really what the definition says, the average squared distance from the mean. But what we can do is we can algebraically manipulate that formula. You don't have to be able to do that for this class, but if you algebraically manipulate it, you can come up with this computational formula, which is n times the sum of the x squareds minus the sum of the x quantities squared over n times n minus 1. And this is the formula that you should use when you calculate this by hand. So if we go through this formula and we plug in, you'll see that the n, of course, is 8. The sum of the x squared. So notice in this case, the squared is inside of the parentheses. And when we sum and square by order of operations, that means we square first, or we always square before we sum. We know that by order of operations. So that means we square the x values, then we sum them. That's what we did in that column to the right, where we squared all the x values. We got that list of squared values, then we summed them. That gave us 11,435. So that's where that sum of the x squareds goes, is it goes right there in the formula where we're looking at the sum of the x squareds. From that, we subtract the sum of the x quantity squared. So notice here the squared is outside of the parentheses, which means we do what's inside the parentheses first. So we sum the x values, which is 301, and then we're going to square that. So we just write that as the sum of x, which is 301. So we write it as 301 squared. The denominator is just n times n minus 1, so that's just simply 8 times 8 minus 1. So that's how the formula works. That's the way it always works. You create these two columns, you get what you need, along with your sample size, and you just plug in the values as you see here on the slide. Once you get that, it's just a matter of cranking through the math. You don't necessarily have to show every step, but I did here. If you take 8 times 11,435, you'll get that 91,480. 301 squared is 90,601. That's over 8 times 7. Subtract, you get 879. 8 times 7 is 56, so that's 879 over 56. That gives us a sample variance in this case of 15.696. Okay, so let's talk a little bit about what this value tells us and what it doesn't tell us. So it's hard to interpret because it is in squared units. So this is not the value that we typically interpret because this is not in the same units as original data. This actually tells us that the average squared distance between the data points and the mean is 15.696. But that fact that it's squared makes it really difficult to interpret. So why do we square it? Let's talk about why we do that. Well, here's the reason why we square it. Because the conceptual formula of the variance is basically you take every data point, you subtract the mean. That gives you the difference between the data point and the mean. And then you square those and you average them. That's the variance. Well, what happens if we don't square them? Well, the problem is, and this is why we use squared values a lot in statistics, is the problem is in statistics, lots of times we reference things off the balancing point. We've already talked about the mean being the balancing point. It is the numerical balancing point of these data values. So what that means is if you take each data point and you subtract the mean, you're going to get some quantity. Well, if you take a data point below the mean and you subtract the mean, you're going to get a negative quantity. If you take a data point above the mean and you subtract the mean, you're going to get a positive quantity. So you get all these negatives and positives, and if you just add those together, they will always add to be the same thing. They will always add to be 0 because the mean is the balancing point. So these negatives and positives in terms of distance from the mean, they're just going to average out, or they're just going to balance out, and they're just going to, when you sum them, go to 0. So that's our issue. Our issue is if we just take the data points and subtract the mean and we add them, we get 0. So we got to get rid of that issue somehow. So one way to get rid of it, you might think, is, well, we could do absolute value, and that is an option. You could take the absolute value of all these differences, and then you could add them together, and that would work. Of course, the thing we don't like about that, if you've ever dealt with absolute value algebraically, you know that it's not very fun to deal with. So we don't really want to use absolute value. So what's another way that we can make all these things positive? And of course, we know that another way to make things positive is to square them. And that's why we do this. So we square them, we make all these distances positive, and then we average them. So we do end up with the average squared distance the data points are from the mean. That's what this quantity represents, which is why it's difficult to interpret, but it's also is a start to where we want to be. We just need to now get rid of the squared part, really. So this is where our last value can... Oh, let me mention one other thing before we move on from variance. Remember that variance is in squared units. This is the other thing I want to talk about. So if you ever get a negative variance, you know what that tells you? It does tell you that you made a mistake. Variance is a squared value. If you square something, it can never be negative. So variance can never be negative. You will never get a negative variance. If you do, you know you made a mistake. Can variance ever be 0? Well, variance can be 0, but only if there is no variability in your data set. So the only way the variance will ever be 0 is if, for example, all your x values or all your data values were all a bunch of the same value. So if your whole data set is a list of 3s and you only have values of 3 in your data set, then that means that the variance is 0. There is no variability. So that means all the data points are 3. The mean is 3. You take every data point, you subtract the mean, you get a bunch of zeros. You average those, you square them and average them, you get 0. So the only way the variance will be 0 is if all your data points are the same. Anything else is going to have some positive variance because then there is some variability in your data set. Okay, so now let's talk about how we get rid of the squared. Well, it's not hard to get rid of a squared, right? We just take the square root. And that's where this last value comes into play. And this is the one we most commonly use. This is the one that we typically interpret. But you have to calculate the variance before you can get standard deviation. Standard deviation is nothing more than just the square root of the variance. The square root of the variance gets rid of the squared, which means instead of dealing with average squared distance the data points are from the mean, we can now, with standard deviation, we now are looking at average distance the data are from the mean. So the way you calculate standard deviation is you just take the square root of the variance. So we denote the standard deviation by s, which should make sense. It's the square root of the variance. So s squared is the variance. S is the sample standard deviation. So S equals the square root of the variance, which in this case is 3.962, and this is the value we typically interpret. So this tells us, on average, these x values are about 3.962 units away from their mean. It tells us, on average, how far the data points are from center. So when you describe a data set numerically, sometimes we use more than 2 measures, but when you use the first 2 measures, we use the mean most commonly and the standard deviation most commonly. The mean tells us where the center is, and the standard deviation tells us how far on average the points are from that center. It accounts for all of your data. That is the benefit of the standard deviation as compared to something like the range. The standard deviation is based on all the data, and we're measuring on average how far the data points are away from the mean or the center of the distribution. So again, most commonly we describe a data set with the mean and standard deviation. So it's important you're able to calculate these values. It's also important you understand what they represent, how to interpret it, how to talk about them, when you should use things like the mean, median, and mode, when those values are most useful. So all those things come into play in this section. The calculations are important, but it's also important to be able to interpret and talk about these values. So that is the end of section 2B.